Artificial intelligence has the potential to solve problems in many different areas, but there are few that can impact each and every one of you as much as your health. There's tremendous potential for AI to help improve outcomes in healthcare. I'm personally really excited about the applications of AI in this area, and I'd like to share with you some of the ways in which AI is helping improve healthcare outcomes. Even though I'm talking specifically about healthcare, some of these principles are actually quite generalizable to other areas as well. So the big shift that's happening in modernizing healthcare, it's towards precision medicine. So on the left here, you have one-size-fits-all medicine, which is kind of the situation today, where scans are manually examined, you have invasive biopsies, and trial and error therapies to figure out what drugs are going to work. All of that adds up to increased costs and worse outcomes. On your right, you have the future with precision medicine, where we can use technologies like radiomics and genomics and come up with precise drugs that are tailor-made for each individual. And we believe that this will result in more efficient spending and much better outcomes for everyone. So what's holding us back from achieving this healthcare nirvana? The first point that we run into is data. There's going to be a tremendous increase in the amount of healthcare data. We expect it to go up by 43% to 2.3 zettabytes. How many of you know what a zettabyte is? Anyone? It's on the order of 1 billion hard disks that exist on a computer today. It's just a huge number. And sometimes the problem is on the other side in terms of not having enough data or not having enough labels to be able to train models that can work with that data. The second issue that we run into is a shortage of specialists. In the US alone, there's expected to be a shortage of 250,000 specialists by 2020. And the third issue I'd like to highlight is the cost of discovering new drugs. Already, it takes 10 years and over $2.5 billion to bring a new drug to market. So how can AI help? We're leveraging the power of deep neural networks to tackle the problem of large data sets. In fact, it becomes an advantage for these algorithms. We're building systems and solutions that can help assist clinicians in their workflow to help them spend their time more efficiently. And we're building algorithms that can help dramatically reduce the costs of drug discovery. Next, I'd like to give you some more concrete examples for each of these. So starting off with deep learning, I'd like to start with this example where we're working with a large medical device manufacturer who wanted to do tumor detection. They were running into problems where their image sizes were extremely large and they would not fit on GPUs. They were having to break apart these images into smaller images and use much smaller batch sizes, which was affecting their accuracy. Using CPUs, they were able to actually fit their data set as well as their model in memory and use much larger batch sizes and get much better performance. In this case, they were using a UNet model, which is a series of convolutional and deconvolutional layers. In addition, there are skip connections that go from the convolutional layers to the deconvolutional layers. So that gives it its U shape. This architecture actually originally came from the autonomous driving world, where it was used for scene segmentation, which actually speaks to the generalization power of these models from one field to another. There were some very interesting algorithmic details as well. I'll just mention one briefly, which is we used transpose convolution instead of upsampling from the original topology, as this primitive had been optimized in our mkldnn library. And overall, we were able to reduce the time to train for this model from a matter of hours to minutes, which was a great solution in this case. So the next example I'd like to give is in the domain of how we're assisting clinicians to use their time more effectively. So this was actually a project we did right here in China with Zhejiang hospitals. There's actually a huge shortage of radiologists here. So there's only 80,000 radiologists to cater to a population of 1.3 billion people. And often the radiologists are actually looking at patients who don't have anything wrong with them. So what the hospital was running into was there were long lines of patients waiting to be seen by radiologists, and there was no good solution. But working together with them, we were able to improve the accuracy of a thyroid detection model from 75% to 85%, which meant that 70% of the work in this case could actually be done by a non-specialist, allowing the radiologist to spend their time on the patients who needed to be seen. So just an amazing example of how this technology can be deployed and bring a lot of value in this field. So this technology has been deployed in 3 hospitals, and 5,000 patients have benefited from the use of this algorithm. And finally, I'd like to give an example in the domain of bringing drugs faster to market. So this example is in slightly earlier stages compared to the other ones, but extremely ambitious and exciting. Here, we were working with a startup based in San Diego called Synthetic Genomics. They were looking to build a model to classify the properties of proteins and discover the function of new ones. We worked with them on this architecture, which actually borrows from the machine translation world, but was able to be generalized to this area. So the input that goes in is basically just a protein sequence, and the output is the function of the protein. What this allowed them to do was find new proteins that could serve as therapeutic agents. Already, they found proteins that would have taken on the order of months and years to find in a matter of hours and days. As I said, this is still fairly early, but this could serve as the foundation for a protein search engine technology where you just go in and type in what kind of protein you want, and you get out a sequence that you can then synthesize in the lab. Solving these problems requires a full stack solution, all the way from optimized algorithms to frameworks, libraries, and of course hardware, both specialized as well as general purpose. Finally, I'd like to leave you with a vision for the future for an AI-based precision medicine platform, where instead of looking at each of these modalities individually, we're actually combining all of these modalities to benefit and get the best kind of solution for patients. For more details, please be sure to stop by my more detailed talk at 4:20 p.m. today in Function Room 2. Thanks a lot.